Hello! And welcome, ladies and gentlemen. This is a 32-bit programmable computer in Minecraft, about twice as many bits as the Apollo space program. And I'm gonna be building it from scratch and at the end use it to compute a hopefully accurate approximation of pi. Now, just to be clear, I am quite certain that this thing is one of the biggest redstone computers ever built. This size, however, isn't a consequence of the computer being particularly special or good. It is built in such an ineffective way that a large size was inevitable. It also takes forever for this bad boy to do anything. So if you know something about redstone computing, please don't have a stroke while watching this video. How big is this behemoth of a construction? Its arithmetic section alone is well over 1,000 chunks or nearing 300,000 square meters, which equates to something like 50 football fields. Football fields, not soccer fields, you American f***. How the fuck are we going to do this? After a quick little Google search, some videos later, I think I got the basics done. Start by creating the ALU of a computer. This part essentially performs some operations on two numbers, so it can add, subtract, multiply and divide, as well as check which number is larger, etc. Once we've built this, we can create some controls for all of these functions, which we'll later use to build our CPU and ROM. And remember, we want to write a program that gives us pi. For this, we'll be using the Leibniz equation. As you can see, we only need to be able to add, subtract and divide numbers. So we want to build a computer. But how? Listen. For this, we'll be using binary numbers, which we can represent with redstone. Every single bit, as it is called, has a certain value. So 001 would be a 1 and 0101 would be a 5. In order to work with fractions, we use something called fixed point representation. We choose our comma to be, say, halfway. Next is sr-latches. These functions essentially store any given binary number when the read signal is on and then output this number to where we want it. In Minecraft, they look something like this. Or at least I thought they did. As you can see, this is quite some work, but I later learned a much simpler design. But this was after I had built all the previous ones. For now, we are building what is known as the ALU of a computer. This specific part usually needs its own memory of numbers so that it can perform all kinds of logical and arithmetic operations on these numbers. For this, a register is used. The 32-bit sr-latch we just built is one register, in our case register A. We're gonna need at least 3 of these. We can now input 2 numbers in our registers, A and B, but how can we now add these numbers together? Listen up, this is gonna be important. A binary adder is used for this. If you want to add 7 and 12, we simply perform the addition by writing down both numbers and adding the first bit of each. 1 plus 0 is simply a 1, so the first bit of our answer will be a 1. We again have 1 plus 0, so also a 1. Following this, we get 1 plus 1. This equals 0 and gives us a carry. Next, we get 1 plus 0 plus the carry, so a 0 again. Lastly, we only get the carry, so a 1. This gives us that 1100 plus 0111 equals 10011, which is 19 or 12 plus 7. We can make so-called half adders, which each only add 1-digit binary numbers together, and then glue these to each other to get a so-called full adder. I initially used the same half adder design as I did in my previous video, a very dumb choice. I later switched to a CCA adder, which is a much more compact version adder I used. There was a slight problem, however. You see, all of these adders were made for 8-bit purposes, which is obviously not gonna be enough. You might say, well, that's no problem, just extend the design. Yeah, no, the Minecraft redstone signals will die out before they reach the top. So I brute forced my way to a proper 32-bit adder design. I know, not pretty and kinda annoying, since our top 8 bits will arrive 4 or 5 ticks later, but it works. Turns out subtraction is basically the same thing. We simply invert the number we want to use and add 1. This is called 2's complement. It's the exact same as normal binary numbers, it's just that the most significant bit becomes negative. So far everything has been going smoothly and multiplication won't be any different. Turns out multiplying numbers is the exact same as adding numbers, just a little bit more. I know I said we didn't need to be able to multiply numbers by approximation, but I forgot about that. We multiply 0, 1, 0, 1 and 0, 0, 1, 0. We simply write down adding 0, 1, 0, 1 4 times, each time shifted one bit to the left. And then, depending on the value of our second number, we enable or disable some of these additions. This means that to multiply two 32-bit numbers, we need 16 CCA adders to start. These have to go into 8 adders, which go into 4, which go into 2, which goes into 1. This definitely took a while, even with world edit, but it works, I think. I haven't tested all different combinations, since there are at least more than 80 different combinations. Division is a cunt. I won't go into too much detail about how the actual process of dividing two binary numbers works, let alone the Minecraft circuit, because I don't give a anymore. Holy shit, this shit cost me 7 years of my life, and it takes 81 working days to compute a division an average 3-year-old can do. Could you compute 1 divided by 2? How about you suck my wait 7 hours and check again a week more of shit? In essence, we use a conditional subtractor a bunch of times over and over again to see whether or not a certain number fits into it. By doing this, we get a resulting number and a remainder. We then multiply this remainder by 2, which means shifting it one bit to the left, and then simply redo the division, giving us the first decimal answer. Since there are 16 numbers behind our comma, we'll have to do this 16 times. There are 2 ways in which you could build a divider. The first one involves using some control logic and a single working divider, and continuously adjusting the inputs and unlocking the output. This type of design can be very compact. Another way of doing things is using a sequential divider. The only problem is that this becomes huge for any large number of bits. This is kind of a brute force method, and for the people who also want to torture themselves by building a computer, I highly recommend Mad Bad Wings' videos. As I was building this Goliath of construction, I decided to obviously test this fucker every once in a while, so I entered 1 divided by 79. Upon getting the wrong fucking answer, I took a look at the individual wires and eventually found the mistake. Oh yep, as you can see, this was pretty fucking stupid. I connected up the 8-bit everywhere in the divider and let it run again. This time, however, the divider did give the correct result. But yeah, 15 hours and 1000 chunks later, we have a divider that is slow as fuck. Because of this large amount of chunks, I also installed a chunk loader mod, so that the divider can actually work. The server usually crashes a couple of times and I have to set the tick rate to 4 for it to run. It does, however, eventually give the right answer. I obviously also added in a basic adder and subtractor to our computer, and when this was done I placed down the registers, the proper ones this time, and connected everything up. This was a shit long process. With all these 17-mile long cables laid down, we could finally move on to the next part of our computer, the control logic unit or CPU. Now that we've got the basics of the ALU finished, it's time to lay down some controls for our PC. Since the different components of the ALU were all over the fucking place, this took quite some time, but eventually I had all of the control signals for the different parts laid out next to each other. Following this, we created the main bus of our computer. This will be used to transport information from our memory banks and ROM to the actual registers of the ALU. With this bus created, we could start work on the CPU of the PC. For this, we'll first create some read-only memory or ROM. This will essentially be where the program we want to run on our PC will be stored. This ROM simply stores a bunch of commands and their appropriate memory target. For example, the command 0011 or 3 will correspond to opening register A and filling it with whatever value we want. Say we want to add 2 and 5 together, we'll store 2 in register A via this instruction and store 5 in register B with this instruction. Next, we'll tell the PC to add whatever the fuck is in these 2 registers together with this instruction. If we now manually unlock each of these parts of the raw memory in this order, we'll get 7 in our C registers. This is great, although actually, it isn't. What if we want to execute a certain instruction bunch of times, such as our Leibniz formula. For this, we'll use a command called the goto command. When this puppy gets executed, the current ROM address that is being handled switches to whatever the f comes after your goto command. So, for the last part of this video, we needed to be able to store the results of our computation somewhere. For this, we needed some random access memory, or RAM. Now hear me out. I was tired, the video had been taking quite some time, I had enough. So, yeah, not the most efficient way of creating 12 bytes of memory, but it works. Almost done. All that's left to do is write the program, put it in, and run the computer. When I sat down to write the instructions for this program, I realized I didn't even have enough instruction addresses, so after upgrading the ROM to be able to handle 64 instructions, I entered in the program, pressed run, set the tick rate to 3 ticks per second, and left. The following morning, I opened up the server, stopped the current execution, looked in the second memory register, and I found this. I then quickly converted this using a calculator and yeah, not even close. It seemed like all hope was lost, but then I searched the wikis, found the Leibniz equation, and realized this number should be equal to pi over 4 and so there we have it, boys, a working goddamn pi approximator, accurate to 2 digits. Obviously, don't take this claim of this being a good PC too serious. It was one of the first times I undertook a project like this, and I didn't even understand the Minecraft tick system properly at the beginning. Again, I highly recommend Mad Bats Wings' videos on Redstone, should you also want to try for yourself. Thank you so much for watching. Goodbye.